You can hear you.
Okay, thank you. So today we are going to look at Bayesian decision theory, and my name is Ankur. And Bayesian decision theory is basically how we can combine probability with machine learning, and it gives us a nice theoretical background framework to look at machine learning. And so let's look at today's contents. Yeah, so first we'll look at how Bayes' theorem is applied to machine learning and how we can minimize what is called the risk when we are taking some decision. And then we will look at some other topics. Now, today's topics might be a bit math intensive and they might look daunting, but don't worry because the final results of all of these topics are very intuitive and we will look at all of them. So our goal is to design a classifier that can recommend decisions that minimize some kind of risk. So the simplest risk you can think of is the classification error. Say, for example, you are trying to classify things into two classes. If you get it right, then your risk is low. If you classify it incorrectly, then you have a high risk. So the risk includes the cost associated with different decisions. So now let's look at some of the terms. So first we look at the state of nature, or which is the random variable. So say for example, we consider this to be omega, and omega 1 can be C bus and omega 2 can be salmon. So so what we are trying to do is our goal would be to identify whether it's a C bus or a salmon based on our observations. And we call this a random variable. So basically, omega can take the value of omega 1 or it can take the value of omega 2 in this example. And then we have some prior probability over omega 1 and omega 2. So this represents our prior knowledge of how likely it is to get a sea bass or a salmon. Maybe sea bass is more commonly available than salmon, so this is our prior probability over which class our data belongs to. And we have a probability density function p of x, which is the evidence. So p of x is evidence. It's called evidence because it's the feature that we observe for it's the feature that we observe. Say for example, our feature can be some a measure of how what is the weight of the fish. So we are trying to classify a fish, so we measure its weight, and that is called the evidence. And it's called evidence because this is what we really observe. And out here we are kind of like detectives. We get some evidence, we get p of x, and based on that evidence we want to classify whether it's a salmon or a sea bass. So yeah, that's why it's called evidence.
So can we pause some for some questions?
Oh yeah, sure. So does anyone have any question?
So someone said, can you be a little louder? Are you close to the mic? I hear you fine actually.
All right. Am I clear now?
I think so. I thought it was clear from the beginning. So one question is, so Bayes theorem basically helps us only for classification problem. Casina, no, that's not true. Bayes theorem can help us with a lot of different kinds of problem. Here we here we are going to talk about the simplest of problems, which is the classification problem. Okay, so here you, uh, the omegas are the class categorical variable, and x is the input, which is whatever input vector, whether it is an image pixels or whether it is like different measurements of the fish or whatever it is. Ram Mohan, you have a question?
Yes, sir. So what is the meaning of state of nature of omega? What does that mean?
So, Ankur, you want to take that?
Yeah, sure. So state of nature is basically what is the actual class that our data belongs to. So a priori we don't really know which class it belongs to. So it can either be omega 1 or omega 2. So it's kind of a random variable because it can take two values, and and the value that it takes is the state. So it's called state of nature.
So can we say that omega is like, let's say, one sample of a fish, and then we are trying to see if it's a sea bass or salmon?
Uh, okay, so you can call omega to be the actual class of your sample. Yeah, I mean not the sample itself, but the class of your sample.
The
Yeah,
class.
so think of this X as not just a single, I mean, there will be different instances of X, right? So for first fish, you will have x1. For a second fish, you will have x2, and so forth.
Yeah.
And they can be either one class or the other class. So let's say they can be omega is equal to omega 1 or omega is equal to omega 2.
And so this was clear for omega, but for PDF, like for which variable, what is the significance of variable x? Like what is it defining?
So basically, yeah, he's coming to that in the next slide. So there will be a PDF of x which will be conditioned upon omega 1 and omega 2. He will come to that.
So I wanted to know what x is in this p of x.
I'm sorry.
What x variable denotes?
X is your input. So X is could be pixels of an image, could be the measurements, for example, length and color and those kind of things. Okay, so that's the evidence. So there
Okay.
is some ringing now noise. I don't know where it is coming from. Maybe uh, yeah, once I mute, maybe it will be better.
Okay, should I continue?
Yes.
Okay, so okay, let me go through the terms once again. So P of x is the probability of getting that evidence. So x is basically our evidence. So it can be some kind of feature that we observe. Say for example, if you are trying to classify a fish, you have to take some kind of feature to classify it. So your feature could be what is the lightness or what is the weight of your fish. So that is x. So based on your observation, you will next try to classify which class it belongs to, and those classes can either be omega 1 or omega 2, and we will look at these in more detail now. Yeah, so and there is another term which is called the conditional probability. So this is p of x given omega j. So suppose you know what is the class that your fish belongs to, then what is the distribution over the features. So say for example, in here we have two examples. We have omega 1 and omega 2. So omega 1 is one type of fish, omega 2 is another type of fish. So if we look at omega 2, we see that the distribution p of x given omega is peaks over here. So we know that most fish which belong to this class 2 have have weight somewhere around 11.5. And if we look at the second distribution, which is omega 1, so if we know that our fish belongs to class omega 1, then there are two peaks. So most fish are either around 13, I have the value of x around 13, or it's around 11. And finally, we come to the conditional probability, which is called posterior, or P of omega j given x. This is what we actually are concerned with. So given we know some feature, we make a measurement over x. So we observe what is the mass of the fish or what is the color of the fish, whatever information we have. Given that information, what is the probability that it belongs to some class? And we are treating this as a probability distribution rather than simply saying that given the feature we get generate a single output, we are instead of generating a single output, we are giving a probability. Say if we measure say a light fish, we can say that maybe it's more likely to be in omega 1 rather than omega 2, and so we get a probability distribution. And okay, now let's look at this case. So if we don't make any observation and we just have our prior probability. So prior probability is P of omega 1 and P of omega 2. How do we decide which class our data belongs to? So right now, if we don't make any measurement and we only have our prior probability, we can choose it based on which probability is higher. If omega 1 is greater than P of omega 2, then we can say that it's omega 1. Otherwise, we say that it belongs to omega 2. And this is pretty intuitive to take a decision in this way. Now, in general, what is the probability that we make an error? Uh, so, Amit sir, should I pause for a question?
Sumit, ask your question.
Yeah, so just this line which is inside the box, Shouldn't it be a conditional probability given
Yeah,
x?
you're right. So we will come to that. So right now we are considering the case in which we don't have any measurement. So and then next we'll come to the case when we have some measurement. Okay, I guess I'll go ahead. So in this case, what is the probability that we make some error? So suppose we decide that our fish belongs to omega 2. So then the probability of error is p of omega 1, because we already chose omega 2. So what is the chance that it was not in omega 2? So then what is the chance that it was in omega 1? And that is p of omega 1. And then if we decide that our fish is omega 1, then it is the p of omega 2 value which is giving us the probability of error. So basically, yeah, whatever is the other class will give the probability of error. Now, if we take our decision based on this rule, our probability of error will become p of, it will be the minimum among p of omega 1 and p of omega 2. This is because we are always taking the larger value. So whichever is the smaller will give us the probability of error. So this kind of decision making favors the most likely class, and it will give the same decision at all times. So no matter uh, what is your data, because you are not making an observation, you are just making a decision based on your prior, you will always make a decision which is based on whichever class is the higher probability. And we can see that p of error can only have two values, p of omega 1 or p of omega 2, based on our decision. And if we take a decision using this rule, we get the minimum of those two values. So given no extra information, this is the most optimal decision that we can take. Yeah. Now let's look at a more interesting case, which is p of omega given x. So if we make some observation, what is the probability of the data belonging to that particular class? And this is where Bayes rule comes into the picture. So we have p of omega given x is p of x given omega into p of omega divided by p of x. And these terms have fairly common names. And this first term is called the likelihood, which is p of x given omega. So this basically says that if we know that our data is coming from class omega, what is the distribution over the features? What is the probability distribution over this value x? And this is called the likelihood. And p of omega is called a prior, because at this point of time we are not having any observation, we are just having our prior knowledge of which class is more likely. And the denominator p of x is called evidence. As we already saw, this is called evidence because this is where we are making some observation. So likewise, if we think of us as machine learning practitioners, who are acting as detectives, we get some observation, we get some data, and that is our evidence. And based on that evidence, we have to decide which class our data belongs to. Now, I hope you guys will remember these three terms, not just for this lecture, but for your lifetime, because they are fairly commonly used terms. So whenever someone says likelihood, you should understand that they mean that what is the distribution over your observed data given your class. Prior is your prior probability, and evidence is the probability of your observed data. And you would have already seen Bayes rule from your pre-read material. And for Bayes rule, we can express the denominator in this form. So we can just sum up over all the classes to get p of x. So essentially, if we have the numerator for all the classes, we can just sum up over all the numerator terms to get the denominator. So now we have some observation. We don't just have to rely on our prior probability to make a decision. So in this case, how do we make a decision? So p of in this case we will use the conditional probability, because now we have extra information. We already know that our data has some particular feature x. So p of omega 1 given x and p of omega 2 given x, and whichever is higher, we will classify our data to that class. Now you can observe that p of omega 1 given x from Bayes rule is essentially p of x given omega into p of omega divided by p of x. And similarly, we can do this for class 2. Now notice that in both of these classes, the denominator is essentially the same thing, because the denominator, which is the observed data, is fixed for both the classes. So when we are making this decision, we can neglect the denominator and consider only the numerator. So essentially, this is how we come to the second decision rule. These two are essentially equivalent. So P of omega 1 given x can be written as P of x given omega into P of omega, and then we divide it by P of x, but P of x is not required. So this becomes our new decision rule. All right, now let's look at some example. So uh, we already
Can we
saw
pause
these
for
two distributions. So if omega 1 was the class, then we get this black curve, which shows the distribution of our features. And similarly, we get a
Uncle?
red curve.
Hello,
Yeah,
hello.
yeah,
Can we pause for a bit?
yeah, sure.
Hey, are you on speaker as
I am not
or
on
are
the
you on
speaker.
headphones? You're
I'm
on
on headphone.
headphones?
Yeah.
Yeah, there is some humming sound that couple of students are complaining about. I don't know where it is coming from.
Uh, Let me check.
So first I thought it's from my computer. I muted myself, it still remained.
I guess my PC is making that sound.
Okay.
Um, just a second.
I wish technology was able to filter these things.
Is it better now?
It's the same.
Okay, that's bad.
Yeah, now it's better.
Now it's better. Okay. Okay.
It becomes better and then becomes worse again.
Mm,
Maybe let's pause for questions.
yeah, sure.
Anyone has questions? Yes, Ramohan.
Um, um, could you explain the likelihood again, that is given the class? The So I was trying to understand what is the meaning of this probability, the probability distribution of the evidence given the class. Does this mean that we are basically trying to see that given this class, what will be the value of each feature depending on various samples?
Yeah, so first of all, is everyone clear that this is not a division, it's a given symbol, it's a vertical line. It's just that when you use italics, it becomes slanted. Everyone should be clear about that. It's conditional probability. Okay. So now if you look at this P of omega j given x, right? So that is the decision that we want to make. So first of all, why are we doing Bayesian based theory, Bayesian based classification? Because this is one of the few ones where the theory is very well developed. Theory of decision making is very well developed compared to several of the other uh, ways of doing machine learning. Okay. Uh, just that for high dimensional data, it is easier to do other forms of machine learning, for example, support vector machines or neural networks. Uh, but from a statistical point, this is a much better developed theory than anything else, and it need not be just for classification. It can be used for regression, it can be used for a lot of other problems where you see dependency between variables using conditional probabilities or joint probabilities. So that's just a little bit of background. So given any input x, right, so given the length and the breadth and the color of the fish, right, you want to find out what is the probability of conditional probability of that being a sea bass or it being a salmon. So class being 1 or 2, omega 1 or omega 2. So that is basically what we are trying to solve. So what we want to do is the decision rule says that we want to compare between P of omega 1 given X and P of omega 2 given X. Or if you have n classes, P of omega n given X. Whichever one is the greatest, that is the class that we will decide. But we cannot compute it directly. The reason we cannot compute it directly is because we don't know how to model P of omega given X. It's something called a generative model. We assume that if we know that the fish is sea bass, then we know that its length is is Gaussian distributed like this, its breadth is Gaussian distributed like this, and its color is Rayleigh distributed like this, or something like that, right? So we know P of x given omega, we don't know P of omega given x. So we know the likelihood, which are the density curves that he drew, that he was showing in the previous slide. And we know the prior because we have done enough fishing to know that you are more likely to catch a sea bass than to catch a salmon. Okay, so you are, let's say, 70% of your catch is going to be sea bass and 30% of your catch is going to be salmon. So your priors are 0.7 and 0.3 respectively. So is this clear, the setting to everyone? Ramohan?
Yes, yes, sir. Yes, sir. So, sir, just one thing I wanted to know, if we were to speak in simple terms for P of X given Wj, that
Yeah.
is P of evidence given the class. Let's say, like, if you would say this is the likelihood of, so what is this a likelihood of?
So remember the which lecture was it where we were modeling distributions, right, using sufficient statistics.
Yes, sir.
So basically that's what it is. You catch all the fish, you divide them into sea bass and salmon. So now you take all the parameters you measure, all the x that you measure for sea bass,
Yes, sir.
you put it into a distribution, you fit a distribution on that, that is P of x given omega 1.
Okay, sir.
You do the same thing for the other one. So you get a red curve and you get a black curve. Okay, red for salmon and black for sea bass, whatever it is.
Yes, sir. Yes, sir.
So
Thank,
that's what it is.
thank you.
All right. Ashish?
Sir, calculating the evidence is always a problem, like I've seen in the literature, right? So,
Yes.
but we always know what is the prior, and we generally play with prior and likelihood, but we kind of, I think this is a problem of evidence, like you cannot compute it. But why
Yes.
is it the case? Because we can know every prior, right? So we can multiply it by the likelihood, and we actually do that. But why don't we? Why? What's the problem in computing px, like the
No,
evidence?
yeah. So the problem is that when you measured the fish and it was 12.3 centimeter, was the fish still moving and it was not 12.3 centimeter, but like some Gaussian around 12.3 centimeter. So we don't really want to model that. That's too much of task to take on. So we set up the problem in such a way that px cancels from the comparison on both sides. Okay, so if you compare p of omega 1 given x and p of omega 2 given x, both are divided by p of x, so that will basically just vanish from both sides. All you have to compare is the numerators, which is p of x given omega 1 times p of omega 1, and compare it to p of x given omega 2 times p of omega 2.
I mean, sir, like situations like conjugate prior and all those things comes, right, where we have to, like, ignore px. So I was
Yes.
asked, like, trying to get an intuition why px is removed from them. Uh,
So this is the simplest way we can model it, right? So here
yeah, yeah,
we
okay,
don't
yeah,
have to assume a conjugate prior or all those things.
yeah,
We just say that we'll set it up in such a way that it
yeah.
just cancels out from all sides.
Thank you, sir.
Okay,
Amit sir, actually, I'd like to add more to
go
your
ahead, please.
answer.
Yeah, yeah.
Yes, I hope my voice is more clear now. Is it?
It's clear, but there's that hum is there. Anyway, go on.
I'm extremely sorry. Okay, so I'd like to add to that answer. So basically, out here we are trying to use Bayes rule to make a decision. I guess the case you are talking about is when we use Bayes rule to learn parameters of our model. So in that case, the denominator, which is the summation term, is actually the summation over all parameter values. Right now, it's the summation over all classes, so we can take it. But the case you are talking about is when we take summation over the feature space, and then in that case this summation is like really huge, and that's why we have to neglect the denominator and use something like conjugate prior that you're talking about. uh, does that does that clarify your question?
Thank you. That works.
Yep. Okay. um, okay, so this was our decision rule. And so on the left hand side we see the prior curves, and on the right hand side we see the posterior curves. So we can see that posterior can have a very different shape from the prior, and if we have some observation, it's better to take our decision based on this posterior. And we will look at the mm, look at an example in more detail in the coming up slides. Okay, so now again coming to the probability of error. So just like in the previous case, so if we decide omega 2, then the probability of error is the probability of classifying it as the other class. And then if we make a decision based on which probability is higher, then our p of error is the minimum of these two terms. Now, this was the probability of error for a particular example, which is just one sample of x. Now, what is the average probability of error over all the samples? So that is basically, we can take this integration, p of probability of, this is the joint probability of error and x, and we integrate it out over all x. Or you can also think of it in terms of summation. So we take the summation over all possible samples that we have, and then this summation can be further simplified like this. So we know that p of the joint probability can be written as p of x into p of error given x. Now we really don't have any control over p of x, but when we take a decision based on which probability is higher, then essentially we are minimizing this error at every step. So okay, I'll tell it once again. So p of at every step we were minimizing the error, because for every sample we were getting the minimum of these two terms, and then so this term is minimized for every x, and then if we take this summation over all x, then the overall summation is also minimized. So in this sense, Bayes rule is optimum because it minimizes the average probability of error. So I see a question.
Hasina, question?
Yes, sir. So, as we've discussed before, uh, the X which we're talking about here, is it a feature or is it a sample in the data? Is it a feature like the length of the fish, the weight of the fish, or is it a sample like containing many features? Is it a sample of the data of the entire data?
I believe it's all the features for one sample.
Yeah, one x is
Okay.
all the features for one particular
Okay.
sample.
And
And
in the graph you have shown us before, you have only represented one feature, is it?
Yes.
uh, yeah, so in this case, we just have one feature, and the x-axis shows the different values for that one particular feature.
Yeah. Okay.
Yeah. Okay, so in this sense, Bayes rule is optimum because it minimizes the average probability of error. Now, where do we, okay, so we were talking about so many probabilities, but where do we get these probabilities in a real world setting? So there are two approaches. One is called the relative frequency, which says that probabilities can only come from experiments. And we can also think of it in the Bayesian approach, which is probabilities can maybe reflect some kind of belief, which need not always come from data. And we'll first look at the first approach, say, and we'll go through it in with an example. So let's say we want to classify cars. So we want to predict whether the price of the car is more than $50,000 or is less than $50,000. So our classes are, one is C1, which represents greater than $50,000, and the next is C2, which is the price of the car is less than $50,000. And the only feature we are using to predict the price of the car is the height of the car. Now we can use Bayes rule to predict the posterior probability. So at test time, we will observe some height, and based on that height, we want to classify what is, either it's in C1, it is whether it's an expensive car, or it's C2, it's not an expensive car. So P of C given X is P of X given C into P of C divided by P of X. So basically, we need the following terms to make our decision: P of X given C1, P of X given C2, and P of C1 and P of C2. And P of X is not really needed, and even if we require it, we can compute P of X using these four terms. And these four terms are basically the terms coming in the numerator of the Bayes rule expression. Okay, so now how do we get these get these values in a real world setting? So we collect data. We ask a lot of drivers how much their car was priced, and we measure the height of their cars, and we can determine prior probability P of C1 and P of C2 based on the number of samples. let's say we talked to a lot of drivers, and then we talked to precisely 1209 drivers, and so we got 1209 samples. And of those samples, we observed that there were 221 cars which belong to class 1 and 988 cars which belong to class 2. So we can already see that most of the cars in our data set were expensive cars, and lesser of them were okay. Which one was expensive? Okay, sorry, most of them were not expensive cars, uh, and only 221 out of them were expensive cars. So then if we compute the probability of class 1, the prior probability, we can simply take the empirical average, which is the number of cars belonging to class 1 divided by total number of cars, and we can do the same thing for class 2, and we get these terms as 0.183 and 0.817. And then we can compute the likelihood, so which is p of x given the class. So how do we compute the p of x given class? This simply can be a histogram. So basically, say, let's look at this case. So we have C1. Where for case 1, we consider all the cars which belong to class 1, and then we compute their heights, and then we normalize their height to, so if we compute their heights, we can already get a histogram over which height is more prominent in that category. And then we can normalize it so that the sum of these heights comes up to 1. And then for C1, we observe that most of the cars are centered around 1 meter in height. And for C2, we observe that most of the cars are centered around 1.5 meter in height. And is everyone following so far, or would you like me to repeat this example? So once again,
Please repeat.
all right, okay. So we want to predict how much the price of a car is, and then basically we want to classify it into two categories. So we want to classify it whether a car is expensive, greater than $50,000, or is cheap, which is less than $50,000. And to do so, we want to use Bayes rule to classify it. So now to use Bayes rule, we need the following four terms, the terms on the right hand side. And what I want to show you is one approach of coming up with these terms from data. So what we do is we talk with a lot of drivers, and then we find out that two of all the drivers, 221 of them had cars which were expensive, and 988 of them had cars which were not expensive. Uh, and then we can say have a prior probability of which of getting an expensive car. So what would that be? That is basically the number of expensive cars divided by the total number of cars. And likewise, we can compute the prior probability of not of inexpensive car, which is the number of inexpensive cars divided by the total number of cars. And so we found out the prior terms. Our next goal is to find out the likelihood term. So the likelihood says that what is the distribution over the height, because in our case the feature x is height. So what is the distribution over height given the category? So let's say our category is C1. So in this case we have a total of 221 cars. So all of these cars will have different heights, and so we basically count the number of cars for each height. So on the x-axis, we have the height of the car, and we divide it into bins. So here we have a bin centered around 1. This might be, I guess, point 0.9, point 0.8, point 0.7, likewise. So around this bin, around say point 0.7, we count the total number of cars, and we plot it on the y-axis. And for height equal to point 0.8, we count the total number of cars, and then put it on the y-axis. And we do it for all of these bins for separately for class 1 and class 2. And then what we do is we take sum over all of these heights and divide each height divided by the sum. So essentially we are trying to ensure that this distribution is a valid probability distribution. As you know, the sum of probabilities should come up to 1. So if you have many terms and divide by their sum, then essentially you can represent it as a probability distribution. So you get so
So
based
hello.
on, yeah.
So you are actually deriving the probability distribution from the histograms. That's why you are dividing the total area, like total number of cars to the each number of column, right?
Yes, total number of cars in each category. So when we are doing it for C1, we will have to divide it by the total number of cars in category C1.
Like in categories, but each column is divided by that number
Right,
separately.
yeah. That's right,
Okay.
yeah. Yeah. And then we do
Right.
it,
So you want to normalize so that you have like you have PDFs,
So that the
right,
probability becomes
normalized PDFs.
one when we sum over it.
exactly.
Yes.
Yeah. And so once we arrive at these histograms, we can see that for category one, most cars are centered around 1 meter in height. So and for category two, we see that most cars are centered around 1.5 meters in height. And now finally, once we have all of these terms, all we needed was we wanted to have our prior and we wanted to have our likelihood. So now we can compute the posterior, which is fairly straightforward. We just apply Bayes rule in its pure form. So P of category one given X, and let's say we make a measurement that X is equal to 1 meter. So what is your probability that it belongs to category 1? So that is P of x given C1 into P of C1, and then we divide and we have to normalize it. So P of x given C1 into P of C1, P of x given C2 into P of C2. And once we put in all of the numbers that we have already computed, we get a value of 0.38. Uh, so now this might be a bit surprising because if you look at the likelihood curve, you saw that most cars in category 1 were centered around 1 meter and most cars in category 2 were actually centered around 1.5. But in our case, our measurement was 1. So if we just looked at the likelihood, we would guess that it should be category 1. Why did Bayes rule say that category 1 has less than zero point 0.5 probability? So if category 1 has 0.438 probability, it means that category 2 has more than half of the probability. So it seems like counterintuitive, but if we go back to our data, we see that although this likelihood suggests that category 1 is more likely, but we also have a prior which says that most cars that we observed were actually from category 2. That's why P of C1 came up to be a small number. And in Bayes rule, we have this multiplicative small factor prior, which is telling us that although we observe that it's 1 meter, it's still more likely that our car is from category 2. So, did everyone get this example so far?
Yeah. Let's pause for
Yeah,
questions. There are some hands.
Just clarify just the one point where you have taken that prior, how you took prior from the histogram, like for that length what is the amount of probab like that normalized histogram length, right? Height, is
are
it
you talking about the prior or the likelihood?
I think likelihood px given
Okay,
some length,
yeah,
x
right.
given some
So the
feature. Yeah,
P of x given the category.
yeah.
So what is your question once again? You
I
want to?
I want to clarify like what is happening there. Get clarified. Uh, that value will be coming from that histogram, right? Like suppose the length is 1 meter, so I will just get the value from that histogram. What is the normalized height?
Right, yeah, true,
Okay,
yeah,
Yeah.
yeah,
okay,
Yeah. This
yeah,
is
that's right.
normalized. That's why it looks taller around 1 meter for category one.
okay, okay. Thank you.
Yeah.
So
I have a
the
doubt.
kind of unnormalized. Yeah. Go ahead, please, Gaurav.
But now we have measurements only for some 10 or 15 points. So like, do we do a normalization, like try to fit some Gaussian, or what? Suppose we want to predict for a different value of x, or we just try to guess it only for this point we have that histogram.
Depends on whether your x is a discrete variable or a continuous variable. If x is continuous, then it will be a your curve will also be continuous. It will not be bar graph. It will actually be a curve that whose integration is
But
one.
but suppose we are just do in a practical case we are just measuring it. Then in suppose let us take we wanted to measure it for some 2.5. Then we'll be like fitting it.
in a Gaussian, or like is there any other way to do that? Is it better to fit it in some
No, so
distribution
it depends
and
on,
try
see,
to fit?
Gaussian is yeah.
Okay,
No, no,
some
you
other
don't have to
distribution.
use a
I'm not
Gaussian.
specific. Ah,
Yeah,
fine.
you
No,
don't
add
have to
like
use a
some
Gaussian.
distribution. Ah, fine.
So,
I get it. Like
right, yeah. So whichever distribution actually fits better, you can use that. You have to use some
so,
knowledge
but
about the problem. Yeah,
okay. So in that case, then we have to fit it to a distribution.
right.
If you want to predicate for some other points which is not in the dataset.
Yes.
Yeah,
Okay.
that's right. And also in your assignment, you will get a question in which you have to exactly do what you just said.
Okay.
Yeah.
Is
So
the
in this
size of the
case, like
bit?
how do we
Go ahead.
uh,
Go ahead.
how do we predict which distribution fits well? Like, is there any? Yes, we just try it out,
Based
or
on that
like how
IIT
is it?
assumption and maximum likelihood. Based on that
Okay.
IIT assumption,
So basic.
maximum likelihood.
Uh,
Yeah, the
so
last lecture
basically,
of
we try out
data
everything.
science module.
Okay. Okay.
Yeah, yeah. So there we had only one distribution. Now we are saying that we have different distributions for different classes. So we are building upon the last lecture of the data science module. Okay. All right. There's a question from Aryan. Is the bin size same for both classes? Yes, in this case it is. And that only then you can make make these comparisons. If the bin size was not the same, then you wouldn't be able to make these comparisons. So you can also have no bin size and actually model it as a continuous distribution. Model X as a continuous variable. Korang?
Sir, actually, I have another question. If it is if the distribution is from a discrete kind of system, like this here it has been represented, then if we fit a certain distribution to that, then will it not be happening that some loss is occurring because of that fitting?
I'm sorry, can you repeat?
Uh, that guy suggested we can actually fit some distribution to that for that class conditional probability. Now
Right.
I am saying if we fit suppose these cars distribution, whether it is class 1 or class 2,
Hmm.
will it not happen ki we are actually losing some information while fitting that distribution to that histogram?
Yes. But that is something that we live with. In entire machine learning, there's a lot of pretty much every technique loses some information. We assume some continuity where there are no points.
But is it not better to just have like we are getting some information, so we are getting some distribution from that histogram itself, so is it not better not to use any distribution, other like standard distribution?
Yeah, so there are other techniques such as non-parametric techniques such as Parson window kernel based density estimation. You can use that also. So that will fit any distribution. So look this up: density estimation using Parson window,
Okay, thank
kernel density estimation (KDE).
you. Okay, KD.
Yeah. Shall we move? Okay. Ankur, let's move.
Okay, sure. So we saw that because we have a prior and a likelihood term involved in our decision, so we have to respect both of them, and then we can compute the posterior. And we did this for x equal to 1. We can do it for all the bins, and then if we do it for all the bins, this is how the posterior curve looks like for this example. So earlier the likelihood looked like this, but the posterior has a very different shape from the likelihood. And again, from this posterior curve, we can see that it dictates that class 2 is more likely if we make an observation of 1, because class 2 is higher in terms of the posterior, while class 2, but in case of, if we just look at the likelihood, then in this case the class 2 was lower in probability than class 1, but if we look at the posterior, then class 2 has a higher probability. All right, so this was one case, but we can come up with a more generic setup in which we can use more than one feature, or we can allow more than two categories, and in we can allow something called action, which is not just classification. We can do something like rejection, and then we define something called a risk, which is basically some kind of cost. So previously we were just considering the risk to be the classification error, but we can have different notation of risk, as we will see in the coming up slides. Okay, so let's define some more terms. So we have already seen that X is a feature. So in particular, it is the feature of one sample, and we have a finite set of categories. So omega 1, omega 2, and maybe more. We can have up to omega C. And then we know that this is the Bayes rule. P of omega given X as P is the likelihood multiplied by the prior divided by the evidence, and we have a finite set of actions. So these actions can be classifications. So let's, for the time being, think of these actions to be classifications. So alpha 1 means that we classify the data to be in class 1, and alpha 2 means we classify the data to be in class 2, and likewise. So then we can define something called the loss function, and we represent it as lambda of alpha I given omega j. So what is the loss associated with taking action I given our data is in category j? So if our data is in category j and we classify it to be in category j, then ideally there should be no loss because we are categorizing it correctly. For all other classification, there will be some cost associated with it. So let's look at a more concrete example. So let's say you use your machine learning knowledge and develop an app in which asks people about some questions like, are you having fever? Are you feeling tired, etc.? And these are your features. You use these features to develop a machine learning classifier, which is a preliminary COVID-19 test with using machine learning. Now, if your app says that a patient is detected with the disease, then the patient is sent for the actual lab test. If it is not detected, then the patient is not sent for the lab test. So your test is really a preliminary test. It's not a final test, but your test determines whether the patient should go for the actual test or not. And this would be the risk matrix for this case. So here on the left hand side, the detected and non-detected, these are our alpha terms. So these are our actions. So your machine learning model can either detect or it cannot detect, and these are the actual categories, the omega variables. So these are your alphas and these are your omegas. So omega is basically either the person is actually affected or actually infected, or the person is actually not infected. Now, if the person is infected and your machine learning model detects it, then the risk is zero because you did a good job. And if the person is not infected and your machine learning model also says it's not infected, then it's fine. There is no cost associated. Now, what happens in now coming up to the interesting part. So if the person is not infected, but still your model says that no, the person is actually infected, so what will happen that the person will be sent for a lab test, and so that's why we associated a positive cost with this. Now, this cost is not really very high because, say, the worst case would be that the person is not infected. Your still model says that he's infected, so he's sent for a lab test, and in the lab test, it will be confirmed that he's not infected, so it's fine. It will just cost some time and money, but it's not a big deal. But if we look at the opposite case in which the person is actually infected, but your machine learning model does not detect it, then he or she will not be sent for the test. And this is really bad because the person will think that he is not infected while he is actually infected. So that's why we have a definition of risk or cost, and this need not always be symmetric. And this particular example shows that cost can be asymmetric. So in our previous example, when we were classifying, we were assigning a symmetric cost based on classification error. Right now, sorry, okay. So right now it can be an asymmetric risk or cost. So, is everyone clear so far?
is risk and loss the same thing in this case?
Yeah, so this particular table represents the conditional risk, which is the risk for classifying taking particular action given particular category. So now if you take the expected risk, which we will see in the coming up slides, that can be called as the loss.
Also, if you go back to the loss function, the lambda loss function, yeah,
Yeah,
in this basically we are saying that if so alpha can be any so alpha, if alpha is j and w is j, then we have no loss, right?
right, yeah,
If alpha is something else and then w is j, that basically means that it essentially was this one class and we predicted that it was another class. So what is the loss, right?
right, exactly, yeah.
So can we interpret in this way that how these classes are different by just like this loss, something like this?
How these
So,
classes are
so
different.
what I'm trying to say is, let's say that let's say we have three classes, one, two, and three, uh,
Okay,
and the w is one, and then for alpha two and alpha three we have losses, right?
right, yeah.
So I'm saying, will they have different losses because they are from different classes, or do we have same kind of losses? Given that the probability, the predicted probability is same of
So
them being
they can have different losses. So for example, let's say you're looking at no disease, pneumonia without COVID and pneumonia with COVID, right? These are your three classes. Then in that case, pneumonia with COVID and pneumonia without COVID, confusing between those two is a smaller risk because both will probably be sent for a lab test. But confusing and either of the two with no COVID, no pneumonia or like healthy is going to be a bigger risk, right? So you need not have, yeah. So the types of errors, if you have three classes, the type of error you make for class one, whether it is class two or class three, for that the cost can be different.
so errors can be based upon the class.
Yes, it can be based upon the class.
Okay, thank you.
So
Hasina,
I want to say something.
go ahead.
So I think that loss risk is depending upon the loss, right? If the loss is zero, then risk is zero. But if the risk is higher, then how the risk like if the loss is higher, then how the risk is calculated, that is depending upon the situation, right? If the situation is more not like it is not acceptable for us, then we will assign higher loss. Like it will obviously be proportional to the loss, that risk, right?
Yeah, right. So it depends on your scenario. Like, yeah, exactly as you said. So if something is more like a more severe problem, you assign a higher risk, and then if it's not such a big deal, then you assign a lower risk.
So loss is something we are like we are assigning, it's not we are
Yeah,
finding
right.
something.
Yeah, that's true. Yeah.
Kasina.
Yes, sir. I am just not able to get the clarity between risk and loss. If you could please explain once.
So for this purpose, I think these are interchangeable. Risk and loss are interchangeable.
So can I simply say that risk is the misclassification error?
Yeah, so that risk matrix that you had, that was that how did we get 10 and how did we get point 0.1? That is subjective. It can be subjective or it can be based on an economic calculation. What is the loss to society of this error versus what is the loss to society of this error? Or what is the loss to company for this error? What is the loss to company for this error? So these are all subjective. It's either subjective or based on some sort of pseudoscience, or not pseudoscience, but some sort of rough calculations. You get some consultant from McKinsey and they tell you some numbers.
Sir, I have a question.
Yes.
Yeah, so can you go back to previous slide? So
This one.
up till now, we were considering omegas as classes, right? What the classifier detects, and here we are telling that omega is correct classification, while the alphas are what the classifier detects. So I got mixed up with this alpha and omega. Can you
So
differentiate?
alpha is your decision. Alpha is the decision that you make. So
Is
alpha
it
is a decided class by the system, and omega is a true underlying class. So
okay?
when alpha and omega are the same, then there is no error.
Okay. So alpha is output of classifier.
Yes, alpha is the output.
Okay.
Okay, let's move ahead.
Okay, sure. So suppose we observe a data point, which is suppose we observe the feature of a data point x and take an action alpha I, and then we have defined that the cost associated with taking action I with omega I being the correct category is lambda alpha I given omega j. So now we can define the conditional risk or the expected loss with taking alpha I as. So say we have this feature which is observed, and what is the risk if we take action alpha I, given we observe this input. So this can be defined, this can be expanded as follows. So what is the probability of that data belonging to some class J, and given it belongs to that class J, and we take action alpha I, what is the risk associated? And then we sum up with over all the classes, because a priori we don't know which class this X belongs to. So we have to sum up over all the classes. So this says what is the probability of that data belonging to some class, and this is the risk. Yeah, and then we take a summation. And in this case, likewise in the so if you go back to the previous examples where we did not have this lambda term, we were just considering the with respect to p of omega given x, and we saw the Bayes rule gives the optimum decision. So if we incorporate risk into the our Bayes rule, then essentially if we express our expected risk like this, and then we take a decision that minimizes the risk, then that is the optimum decision that we can take. Okay, so now we are claiming that Bayes rule gives the optimum decision in the sense that it minimizes the risk. So Bayes rule, when we use Bayes rule, it computes the risk of alpha I given x for every alpha I. So so here it was written as summation, but yeah, so okay. So this is first we obtain the risk using this expression, and then we sum up over all possible samples in our data set. So this will give us the overall risk. So this is risk for one sample, and then if we integrate over all axes, then we get the total risk over our data. So when we use Bayesian decision, we minimize this risk for every sample, and since it's minimized for every sample, it's the overall term is minimized when we use Bayes rule. So the risk that we obtain using Bayesian decision is the risk that is the optimum value of risk that we can obtain. Okay, now let's look at one more example. Suppose we have two categories. We define the categories as omega 1 and omega 2, and then we have our actions. So alpha 1 means we decide that it's omega 1, and action 2 means that we decided to be omega 2. And then we have our risk matrix, which is lambda of alpha I given omega j. So the risks are, so as we already saw, the conditional risk can be expressed with this expression. The risk of taking action I given we observed some feature. So it is summation over all possible classes, and in the summation we have the risk term and the probability term. And if we take this summation, say for risk of taking action one, given we have an observation, it will come out to be lambda 1 1. So both of them will be 1 1, p of omega 1 given x plus lambda 1 2, p of omega 2 given x. And similarly, we can compute the risk associated with taking action 2, that is lambda 2 1 multiplied by probability of omega 1 given x, and lambda 2 2 multiplied by probability of omega 2 given x. If you look at the terms carefully, so lambda 1 1 is saying that your actual category is 1 and you are calling it to be category 1. So the first term is your action and the second term is the true class. So lambda 1 1 is the risk associated with that case, and then you multiply it with the probability of belonging to class 1. So if your data actually belongs to class 1, you weigh it with the risk of actually classifying it as class 1. And ideally this lambda 1 1 would be 0, so this term will come out to be 0. And the second term is saying that what is the probability of it being belonging to class 2, and this is the risk of classifying that data which belongs to class 2 as a data point belonging to class 1. So this is the risk which is the information you give to your model, and this is the probability of belonging to class 2. So essentially risk of taking action 1 given the data point is basically what is the probability that it did not belong to class 1, so the probability that it actually belonged to class 2, and then the weight that we assign for that particular decision. uh, Amit sir, do we have questions?
Yeah, Kasina, what's your question?
Yes, sir. So, I wanted to make this clear. Like, I wanted to get it clear is that, like, before we use the term error, right? Conditional error or whatever. Now,
Yes.
now we are using risk, right? So, is it that to be more precise and more uh, for the model to be more optimal, we are using this risk, or are these two terms completely different?
So these terms are related. Here, what we are saying is that the two types of type 1 error and type 2 error are not the same. We are saying one has higher risk than the other.
No, didn't get you on that point. Could you
So
please?
type 1 error and type 2 error, false positive versus false negative, right? We are saying that they are not the same. They carry different risks. Their cost associated with making the two errors is different. So if we just use the term error, then we lose that sight that there are different types of error: false positives and false negatives.
Okay, okay.
Okay. So here we are saying no, we are going to distinguish between false
Uh,
positives and false negatives as well. Okay.
okay, sir. Thank
All right. So let's take Abhinandan.
Yes. So when we say lambda II, that is the diagonal in the lambda matrix, lambda 1 1, lambda 2 2, that will always be zero, or will that be any possibility that it will be non-zero?
I have never seen it not being zero, but I suppose you could have a. But I don't know why would you would not have
Be zero.
zero. Yeah, it doesn't make practical sense.
Yeah.
Ram Mohan.
So for the overall in the slide in which it shows overall risk, I wanted to know why we are doing an integral because from my understanding, x is a feature vector and feature vectors are usually discrete. So the integral part, I'm not.
No, no, feature vectors can be continuous, right? So let's say Px was not a delta Dirac distribution. If we measure x and we are very sure of x and there is no confusion about x, then this is a simple thing, right? Then all you do is r of ax given x, that's it, at that particular x. But let's say if x was diffused, p of x was diffused. So usually we assume p of x to be a delta Dirac distribution, or we don't want to deal with it. So here we are assuming that there's a distribution over what you observe also. The fish was not 12.3 centimeters. It was 12.3 centimeter plus minus 0.2 centimeter, some Gaussian around 12.3 centimeter.
Okay, sir. Okay.
Yeah. So it makes it like even more Bayesian, like add one more term here. So, right? Okay.
Hmm.
Sumit?
Yes, sir. So regarding x, so more often than not, it will be a vector, right? So
Yes.
while calculating the conditional probability, can you go to the next slide? Where yeah, so no, where it is probability of omega by x conditional. Yeah. So while
Omega given x. Huh?
yeah,
No, don't say by
calculating
x.
these
Please say,
conditional probabilities.
yeah.
So we'll be using the fact that this x as a vector is an IID vector elements, and then we will multiply those probabilities
So, so what is IID? IID is between samples.
Okay.
Okay.
So,
One sample is IID, like samples are IID with respect to each other.
but
That,
suppose x is a vector length, height,
but
weight.
each x is a vector,
Yeah.
and their features may not be independent. A bigger fish is both broader and fatter. There's no, it's not like in the width and the height are independent of each other.
Then
It's
how
just
do
one
we
fish is independent of the second fish.
how we compute p omega j by x, where x is a vector?
We can't. We have to compute it using Bayes rule. We have to make actually p of x given omega times p omega divided by p of x. So we actually cannot compute p of omega given x. We have to, that the first part of the lecture, that equation we'll plug in here.
Oh, okay. Okay.
Manan, what's your question? Please explain conditional risk again. Ankur, can you take that?
Sure. Okay, the conditional risk says that, yeah, so the conditional risk says that we make an observation of a feature for one data point, and we take an action AI. So what is the risk associated with taking that action AI? So now if this our data feature is X, we don't really know what class it belongs to. So we have to consider the case that it belongs to all. So we have to consider it in terms of a probability that it belongs to every class. So we have a probability of X belonging to class J, omega j, and then we sum up over all the classes. So some of these probabilities can be high, some can be low, but we have to consider all of them, and then we multiply that probability with the risk associated of taking associated with taking action I given it belongs to class J. So, and then we have to sum up over all the classes. So the first term is saying that what is the probability of the data point belonging to the some class, and given the data belongs to that class, what is the probability? What is the risk of taking action AI? This, and then we sum up over all the classes. Um, is that clear now?
So I want to ask you a question.
Yeah,
Hello.
sure. Yeah,
So initially we were developing these equations and all concepts for a single feature. Now we are setting up things like for real world scenario we have multiple features. Now we want to take a decision and have like get the risk and all those things. That's why you are
right.
using that vector x, right?
Yeah, right. Yeah.
Okay.
Okay. So then I'll move ahead. So we obtained these two conditional risk terms for taking action A1 and taking action A2. So now our goal would be to minimize the risk. So to minimize the risk, we will select omega 1 if the risk of taking action A1 is lower. Otherwise, we will select omega 2. And in these risk terms, we have already derived the expressions over here. So if you just simply manipulate these equations, this is exactly equivalent to this. So you just have to move the term from the left to right and right to left, and you arrive at this rule. So you can use this decision rule to so as to minimize your risk. And this is also equivalent to the following. So if you just divide the lambda terms, so if you bring this left hand side over here, you can get this expression, and then you divide omega 1 by x and omega 2 by x and bring it over here, and then you expand omega 1 given x as omega x given omega, sorry, p of x given omega into p of x into p of omega. So you get these extra terms. So so essentially all these three rules are exactly the same, and you can use any of these rules to make your decision. So this says that you decide your class to be omega 1 if this likelihood ratio is above a particular threshold. And what determines this threshold? So in this threshold we have the probability terms which are coming for p of omega 2 and p of omega 1, and these are your priors, and these are the terms which come from your risk. So if your likelihood ratio crosses this threshold, then you classify your data to be omega 1, otherwise you classify it to be omega 2. Yeah, and maybe you can derive these equations after the lecture by yourself. It's quite straightforward. Uh, okay, so now we can look at some special cases. So this is basically assigning the same loss to all errors. So if you say if your actual class is omega j and you classify it uh, to belong to class I. So if I is equal to j, then there is no cost. If I is not equal to j, then the cost is 1. So you don't really discriminate between the different classification losses. So this is the most simple case. So essentially, if you now derive the conditional risk, we have already seen this expression. Now in this expression, you can clearly see that we are summing over j, and in this summation, there will be just one term when j will be equal to I. In that case, this will be 1. In that case, it will be 0. And for all other cases, this will be 1, because we are saying that this lambda is 0 only when I is equal to j. So this is essentially you are summing up over all terms p of omega j given x, except when I is equal to j. So for I not equal to j, you are taking a summation. Now from we know that probability should sum up to 1. So this is equivalent to 1 minus p of omega I given x. Now, if you look at this expression, this is extremely intuitive. So what is the risk associated with taking action I given your data? That is 1 minus probability of that that category given your data, given your feature. So if your probability if the probability of that data belonging to that class is high, then 1 minus that probability is low, and that says that the risk is low. So if your actual probability of belonging to that class is high, then the risk is low, and vice versa. And then if you again, if we are deciding, we are making a decision rule based on risk. So if we basically we want to minimize risk, so if we want to minimize risk, we want to maximize the probability. So if we, in this case, we see that the overall risk is same as the overall probability of error. So for this case, this is a symmetric case in which we assign the symmetric basically risk to all misclassifications. It is same as the average probability error, or like misclassification error. And let's see like and there is one more thing which is called decision regions. So we saw that our decision can this was our decision rule. So if the likelihood ratio is above this threshold, we classify it as omega 1, otherwise we classify it as omega 2. And based on this, so this is written here once again. So so this term we are calling this threshold to be theta, and then we are considering two cases. So if we consider the case in which these lambdas are symmetric, so essentially we are saying that lambda 1 1 and lambda 2 2 are 0, these two terms are 0, and lambda 1 2 and lambda 2 are exactly equal. So then this expression cancels out, and we are left with p of omega 2 and p divided by p of omega 1, and this is one case which is theta A. Now, and theta B considers the more generic case in which a threshold value is this. And let's say when we compute the likelihood, so p of x given omega 1 and p of x given omega 2, and we compute the ratio of the likelihood, and then we plot it. And let's say theta A is over here and theta B is over here. So when we consider the case for theta A, so we can draw a line like this. So the regions in this curve which are above this threshold would be classified as omega 1. So from here to here, this curve is over the threshold, and again from here to here is over the threshold. So, and these are classified as 1. So this is region 1, and this is also region 1. And the other regions in which the curve is below this threshold would be classified as the second category. Okay, another useful way to represent.
Let's take some questions.
Okay, sure. Yeah.
Any questions? Okay, no questions. Let's move.
Okay. So another useful way to represent classifiers is through discriminant functions. So previously we were saying that we would use risk to minimize our, we would minimize risk to classify, but we can use something else, a more generic thing, which can be called as our discriminant function. So we have a function gi, which is a function of the feature. So let's say, let's look at this figure. So we have d features, x1, x2, x3, xd. So we have a feature which is a vector of d dimension, and then we have g1, g2, g3 up to gc. These are our c discriminant functions, and each of these functions takes as input all the features. So g1 takes as input all the features, g2 also takes as input all the features, and so on. And based on these features, this function computes a value which we call as the cost. So basically, uh, just a second. Yeah, so we can treat it in other ways as well, but in this case, in this discriminant function, what we are trying to do is we are trying to maximize the output of these functions. So, for example, for if we feed in some particular feature input, and then we compute the outputs of all of these functions, and whichever gives the highest value, we call that particular we classify our data to that particular class. So it says that if gi of x is greater than gj of x for all j not equal to I, then we classify our data as I. So one particular example of a discriminant function can be the negative of risk. So if we are trying to minimize the risk, essentially we are trying to maximize the negative of the risk. And another special case could be when we considered symmetric risk values. In that case, our risk was essentially 1 minus the probability. So if you have minus risk, it comes out to be p minus 1, and that minus 1 is same across all the discriminant functions, so it can be included neglected. So it comes out to be the probability, and this is very intuitive because if the probability of the data belonging to some particular class is higher, then we will classify our data to that particular class. Yeah. Another thing that we can do with our discriminant functions is we can feed in our discriminant function to through a monotonic function. So monotonically increasing function. So a monotonically increasing function is basically a function in which if you feed in a higher value, the function will give you a relatively higher value. So curves like log of x are monotonic function because if you take any value log of say 5 and log of 2, log of 5 is greater than log of 2. So if the input is higher than the output, input is higher, then the output is also higher. So so basically in our decision we are only looking at the relative values of all these discriminant functions. So if g of I is greater than g of j and we feed in g of I to a monotonic function, say log, so log of gi will also be greater than log of gj, so our decision rule does not change. So why are we doing this? It's basically sometimes it might help us in our calculation to use a monotonic function uh, uh, at the output of our discriminant function, which will simplify our calculation. And we will look at an example of this. Uh, yeah, so okay, now let's look at the case when we just have two classes and we have two discriminant functions g1 and g2. So instead of using a rule in which we compare g1 and g2, we can consider a single discriminant function which is g1 minus g2. Now if g1 is greater than g2, this term will be positive, and if g2 is greater than g1, this term will be negative. So we can just look at their difference to classify. If so basically if g of x is greater than 0, then we classify it to be 1. Otherwise, we classify it to be 2. And maybe one example could be, so if p of omega 1 given x and p of omega 2 given x were our discriminant functions, so we can consider a single discriminant function which is a subtraction of the two, And then also we can, instead of using them directly, we can pass them through ln. So ln is log base e. So we can pass them through the log function and then consider the discriminant function. So yeah, so basically you put in log over here and log over here, and then you simplify it and get this expression. Okay.
Can let's pause for a bit. There's a question. Can you explain the first slide of discriminant functions again?
Okay, okay. I will explain it again. So a discriminant function is basically, it is a function which will give a value that will help you make a calculation. Basically, that will help you classify your data. So if you have, let's say you have C classes. So you will have C discriminant functions G1, G2, G3, and GC. The value of each of these functions depends on all of their features, x1 to xd. Now, so if you feed in some feature that you observe, say you observe some particular height, some particular color, some particular size, you feed in all of these features, each of these discriminant functions will give you a value. Whichever discriminant function gives you the highest value, you classify your data to that particular class. If G1 give the highest value among all of them, you will say that your data belongs to class 1. And this is basically one particular model that you can use to make your classification. Is that clear?
So basically, you will have one discriminant function per class, and they will each discriminant function will take the same input, and the one that gives you the highest value, that is what you will decide the class is. So you will see this structure again in sort of like a neural network where your final layer is sort of like a discriminant series of discriminant functions. Ram Mohan?
Yes, sir. So I'm trying to understand the bigger picture here. Like initially, what we were doing were we had prior probabilities of things, then we introduced evidence, and then we got like what is the probability given this evidence. Then we introduced the concept of risk. So I'm trying to understand first why did we introduce the concept of risk, and now this discriminant function. Like what do these things solve that we introduced in?
Yeah, so let's say if we assumed all classes were equiprobable, then we would have just looked at class conditional, P of omega j given x. Okay, that's the simplest form. Then we assume that classes need not be equiprobable. P of omega 1 and P of omega 2 need not be the same. So we'll use Bayes rule to now compare P of omega j given x times P of omega j for different j's, right? So that's the next level of complexity. Third level of complexity is even the errors are not symmetric in cost. So we will also add error and then compare it. Okay.
So the last one was for discriminant, sir. So the errors are not consistent.
Basically, the common theme is that if we generalize this further, basically what we are doing is we are comparing some function g1 or gj of x for each class j. Okay, so that function, discriminant function, is taking different forms. It takes either just the class conditional, or it takes class conditional times the prior, or it takes class conditional times the prior times the risk, the difference in this, the lambda differences and so forth, right? So it becomes increasingly more complex, and even but ultimately we are comparing, let's say, one function for each class, and the one that gives you the highest value is what will help us
So your voice is not audible.
So I'm saying that the is it audible now?
Yes, sir. Yes.
So I'm saying that the common theme is that you have a one G function for each class, one discriminant function for each class. Okay. So which is shown pictorially here.
So you learn this G function for each class? Do we learn this G function or do we
Yeah,
assign
yeah,
it?
yeah, absolutely. We learned this function, right? P of x given omega is learned by fitting a distribution over x for a given omega,
Yes, sir. Yes, sir.
right? So it is learned.
So then during testing, when any sample comes, we pass it through every function, and whichever gives the highest value, that's how we see which class it was.
Yes.
Okay.
Okay, so then another question is, do risk act like prior? I mean, not exactly, right? Prior has a specific meaning. Prior means how likely is one class. Risk adds in another factor or multiplies another factor, which is which error is more costly, which error is riskier. So prior all just means a probabilistic notion. Risk means cost. Okay. Goran?
So earlier we are assigning that risk value for each action, like for each misclassification of action, we are assigning some value. Now with discriminant function, we are learning that function from certain input output, right?
So we haven't specified how we are learning it just yet.
No,
We are
no,
just saying that
I'm
there's a concept of a discriminant function, and this the the three different types of model: the model that does not take prior, the model that takes prior, and the model that takes both prior and the risk. They are all fitting into this description of a discriminant function.
No, I was asking whether that is the same thing. Like we are assigning that risk value for each misclassification.
Yes.
We are modeling it with a function.
Yes.
Okay.
Siddharth?
Sir, just to clarify, we are giving the input x1 to each of the discriminant function and then comparing whose value is the greatest.
Yeah, that's right.
Yes.
Based upon that, we'll take the classification, right?
Yeah, right.
Okay, thank you.
Okay. Let's move ahead.
Okay. So as Amit sir already explained, so discriminant function is a more generic picture. So we have some functions, and whichever function gives the highest value for our input, we classify it to that class. And this discriminant function can take different forms. So one form can be based on the risk. So we in the risk case we wanted to minimize it, but in this discriminant function we are trying to maximize a function. So we can simply use minus of risk as our discriminant function. And another discriminant function could be the probability itself, the posterior probability. So that is probability of belonging to particular class given x. Okay, and the other thing that we looked at is using a monotonic function at the output of our discriminator. So since discriminator only considers the relative values of these outputs, it does not care what is the actual value of G1, G2, G3, Gc. Considers which is the highest, or the in the relative sense which is higher. So if you pass it through a monotonic function, that does not change the order of the input. So log is one such example. Then if you pass the discriminator through log, then it is still a valid discriminator function. So, and here was one example. So if we use the posterior as, yeah, okay. So here we looked at another case, how we can, if we have two classes, we don't have to really look at two discriminator functions. We can take the subtraction and compare whether it's greater than zero or less than zero. And say our discriminator function is the posterior distribution. So it will come up like this. And instead of this, we can also use pass it through the log function and use that as the discriminator. Okay, now let's look at Gaussian distribution. And in your PDF material, there was already a content for Gaussian distribution. So in one dimension, the Gaussian looks like this: 1 by root 2 pi sigma square e to the power minus x minus mu by sigma whole square divide by 2. Yeah, divide by 2. So what they say in this expression, this is a distribution over all x. This is what this equation says. So if you plug in some value of x, it will tell you what is your probability of getting that x. And inside these the two things that matter for Gaussian are its mean and its variance. So mean is mu and variance is sigma squared. Sigma squared, yeah. And yeah, and the above term can also be written like this. So this was the Gaussian for one dimensional case. We can also generalize it to multidimensional case. So this inner term can now be generalized like this. So these x and mu, instead of being scalars, they can be vectors. So you replace them with vectors. So x minus mu, and this dash means transpose, and then your variance will now be a matrix. So if your input is n dimensional, your variance will be n cross n dimensional. Okay, here they are saying p dimensional. So if your input is p dimensional, your variance will be p cross p dimensional, and this is the inverse of that variance matrix. And then you multiply it with x minus mu. So this is the expression for Gaussian in n dimensional or p dimensional. So you have instead of so the denominator changes to, here we have a determinant root over the determinant of the variance matrix, and over here we have 2 pi to the power p by 2, and the inner term looks like this. Okay, so maybe I can show how it looks like by plotting it. Okay, so here is how Gaussian looks like in one dimensional. So here I have defined a function that gives us the probability for 1D Gaussian. So it takes in the value of x, the mean, and the sigma. And then first we compute the numerator term and then the denominator term, and then we divide them. So if we take values between -5 and 5 and plot the Gaussian, it looks like this. So in this case I have assigned mu and sigma to be 1 and 1. So you can see that the peak is at 1 because the mean was 1, and this variance term the sigma, or sigma square is called variance, so sigma is the standard deviation. So that determines how wide your Gaussian looks like. So say if I make it like 3, it becomes a wider Gaussian. And if I make it low, then it becomes a narrower Gaussian. So instead of writing the function yourself, you can also use SciPy to plot the Gaussian. So SciPy provides multivariate normal.pdf to generate multivariate Gaussian distribution. So here I have, you can just pass the mean and the covariance, and we get exactly the same plot as before. So now this was a simple one-dimensional case. What happens when we look at n-dimensional? So again, I'm using SciPy to generate these distributions. So first, so first here I'm defining the mean as 0, 0, and this is the covariance matrix. So now let me use a simple covariance matrix. Okay, so for this covariance matrix, this is how your Gaussian looks like. So I'm using a two-dimensional mean. As you can see, the mean is 0, 0. So it is two-dimensional, and your covariance is now 2 cross 2-dimensional matrix. So I'm calling the first dimension as x and the second dimension as y. So if you look at the plot, this is the x-axis and this is the y-axis. And at 0, 0, we see a peak for this Gaussian. And on the right hand side, you see what is called the contour plot for the same distribution. So this shows, you can imagine it's a top-down view of this hill-like figure. So if you look at it from top, so points of same color have similar values, and this is a color map which shows the values. So it says that at 0, 0, you have the highest value, highest probability, and as you go further away from the center, your probability decreases. And further out, say in the outer region, the probability is pretty much zero for that value to take place. So maybe we can change these values a bit. So let me increase the covariance. You can make it 3. So now if I increase the covariance, we see that the hill is more spread out. So we see a bigger circle over here. We can also do things like we can make it more skewed along one axis than the other. So in this case, the covariance value for x-axis is less and for y-axis is high. So you see that it's kind of skewed. So x covariance was low. So the variance along x was low. So it's thin on this axis, and along y it was high. So it's elongated along this axis. And you can also see it from this plot. And uh, you can also make the plots not be axis aligned. So what I mean to say is this. So earlier we were only considering diagonal covariance matrices. So if you use a diagonal covariance matrix, you will get plots, you will get ellipses in the contour plot which are axis aligned. But if you want to rotate this ellipse, so you can add values to the non-diagonal elements. Okay, it's not big enough. Yeah, so now in this case we get you get a Gaussian which is not aligned to the x and y axis. So yeah, so feel free to play with different values of mean and covariance and see how the Gaussian looks like. Okay. So so the reason I showed the Gaussian plots is because we can use the Gaussian to model our to we can use the Gaussian distribution as our machine learning model. So, for example, if we have a mean and a variance, this is how the normal distribution looks like, normal or Gaussian distribution. And we can use this as our discriminant function. So we say that, uh, yeah, the discriminant function is basically the log of p of x given omega I and the log of p of omega I. So yeah, so or you can think if you get rid of the log, then this is essentially p of x given omega multiplied by p of omega, which is equivalent to the posterior distribution that we were using as a discriminant function. So we are just putting a log over here, and the reason we put the log is because in the normal distribution we have exp over here, and log and exp cancel out, and that simplifies our calculation. So this is how our discriminant function looks like. So use if we put this expression in our Gaussian, so we get so this log, so this exp cancels out, so we have minus 1 by 2 x minus mu. So all of this term comes from here, and then this 2 pi comes down to here, and then this variance comes to here. So these are the three terms we get from this distribution, and this extra p term is coming from our prior. So essentially, this normal is modeling our is modeling our likelihood. So p of x given omega is modeled using this Gaussian, and then we have our prior, and if we multiply the prior and the likelihood, we can get the posterior, um, and then we are taking a log to simplify our calculation. Okay, now this was our discriminant function for the Gaussian case. Now let's look at some special cases. So say our data is one dimensional, and oh, okay, sorry, not one dimensional. Say our data is multidimensional, but our covariance is fixed for all classes. So sigma I for the covariance for ith class is a diagonal matrix whose entries are sigma square, this small sigma square, and it's fixed for all the classes. So since in the discriminant function we only care about relative values, so you can see that this term does not matter because it will be same no matter what is your I. And we already said that this sigma is same for all i's, so this is also same for all classes. So only remaining terms are this first term and the last term. So our discriminant function looks like this. So what do these terms say? So this second term says that we are favoring the class which has higher prior probability. And the second term says that we are favoring the class that is whose mean is closer to our observed data. Okay, and this inner product square can be expressed is basically this. It's written in short form. So, and then if you do some manipulation over the variables, you can expand this GI and then finally express it in this form: omega I transpose x plus omega I 0. So where omega I and omega I naught are expressed in this way. So if you think of this as the GI, so you're and you want to look at what is your decision boundary. So what is essentially a decision boundary? A decision boundary is where you are basically the boundary point between two regions. So if On the left hand side of that region, you will classify it as one class. On the right hand side, you will classify it as the other class. So in this case, since we get a linear function over here, and if we want to find out the decision boundary between class I and j, so the decision boundary will be given by those points in which these values are equal, because at the boundary they will be equal. On one side, one of them will be larger, and on the other side, the other one will be larger. So if you set them to be equal, from this expression, again, you can simplify the values, but you get a form like this. So this says that omega, this omega t multiplied by omega transpose multiplied by x minus x naught is equal to 0, gives us the decision boundary. So x is our feature, and omega t, omega, and x naught are constants that we get from our model. So wherever this is 0, we get our decision boundary. So since this is a linear function, so in 1D it will look like a line. In multidimensional, it will look like a plane, or say in, and then if you go to higher dimensions, you can get what is called a hyperplane. So there. Uh, so Amit sir, do you think we should stop for some questions?
Yes.
Yeah. Okay.
So one question was, is the covariance matrix assumed to be uh, diagonal positive semi-definite because of ease of computing the inverse? No, so covariance matrix is assumed to be diagonal for convenience, but in general it is assumed to be symmetric and positive definite, positive semi-definite. Not assumed, it is positive semi-definite by definition, and it is symmetric by definition, because covariance of x and y is same as covariance of y and x. So your diagonal elements, off diagonal elements will be symmetric. Any reason for mapping it to Gaussian? Yes, the reason for mapping it to Gaussian actually is convenience. And also, if you have some insight about the process by which the data was generated, if you look at the data distribution and it looks like Gaussian, then you assume it to be Gaussian. But general analysis, Bayesian
Sir, you are
analysis.
not audible.
Okay, hold on. Give me a second. Let me wear my headphones. Is it better now?
Yes, sir.
So I was saying that we assume Gaussian densities because a lot of data is actually Gaussian distributed, but there is no reason to stick to Gaussian. The entire Bayesian framework is applicable to non-Gaussian densities also. Okay, just that just that the distribution will look different. Okay. And okay, Ramohan, you have a question?
Yes, sir. So I have a question, but you were not audible. I think you were breaking off with the mic in the last question too.
Is it audible now?
Yes, sir, it's audible now.
So I was saying that so I was answering the question by Aryan. Why assume the densities to be Gaussian? The reason to assume Gaussian is usually Gaussian is very well studied, and a lot of natural distributions are indeed very close to Gaussian. But it's a good question to ask whether a data is indeed Gaussian distributed. In many cases it is not Gaussian distributed. So only your class conditional densities will change. Rest of the analysis, the structure of the analysis will remain the same. Okay, so there is no hard and fast need to assume Gaussian, just that the math for Gaussian is very well developed. That's a mathematical convenience.
Yes, sir. So
We are
my
taking an example distribution for like further proceeding the math.
Yeah, so for example, if you are measuring length of a fish, it cannot be Gaussian because Gaussian extends to negative infinity also. Length of the fish cannot be negative infinity. Okay,
No,
and
I am saying so we are just taking Gaussian as the distribution to further proceed how we are developing all the things. Just that
right,
for that.
it's
For
just
if the
it's
case
an
is different, then we have to do that.
yes. So if it is indeed non-Gaussian, then you assume some other distribution that fits the data better.
Oh.
Ramohan, any other question?
yes, sir. So the statement where it is written that the p of x given wi omega I is tilde from normal, mu, and then the variance. Um, so, like, what is the meaning of this? I don't understand the
It's
meaning.
it's distributed as normal of that tilde means is distributed or is sampled from a that's what it means.
Okay, sir. So,
Okay.
did we? Uh, is this the same thing that you answered before? Like, where is this coming from? We are just assuming this, or we
We are
just
just assuming. We are just assuming that it has mu I and sigma I and it is Gaussian distributed.
okay, sir.
Okay. Uh, Ashish is asking how is the boundary line derived. So boundary line is derived where P of omega 1 given x is equal to P of omega 2 given x. That's pretty much it. Where the one discriminant function is equal to the other discriminant function. Otherwise, one of them on one side of the boundary gi will be greater or other side gj will be greater. So boundary is where both classes are equally probable. That's the decision boundary. So for any classifier, it is good to know what the decision boundary looks like. So here, if you assume Gaussian class conditionals, then your decision boundary will be some sort of a quadratic curve or quadratic hyperplane. And when your covariance matrices are the same, then it will be a linear hyperplane, which is a subset of quadratic. Shubham?
Yes, sir. So when we were finding this decision boundary, we were equating both the cost function and we were finding the points which are same. So I understood that it's mathematically fine to do that. But what about these points? If we think, so which class will these points belong to? Because they are lying in both of them, no?
So first of all, no, I mean that's not a good way to think about it because any point in a continuous space is infinitesimal. Its probability is zero. This is what we tried to cover in the first in the statistics lecture. That never think of in terms of a probability of a point in continuous space. It will always be zero. So if you are really bothered by what will happen if it actually lands on the boundary, then you can have some arbitrary rule that I will assign it class 1 or class 2. There is no reason to argue that one rule is better than the other.
Okay, sir. Thank you.
What is the significance of using dichotomizer? I missed that. So maybe Ankur, can you answer that? Oh yeah, that one, dichotomizer. So there basically we don't have to compute two functions. We figure out what is this function g of x by just taking the difference of the two functions. If you have only two classes, one function will do and you just compare it to zero. Okay, so it reduces your function computation from computing g1 and g2 as two separate functions to a simple function which is g. Okay, Ram Mohan.
Yes, sir. So, if you go to the decision boundary slide, yes, sir. Sir, how are we concluding that the decision boundary for two axes could be quadratic?
So here the quadratic term disappeared because the quadratic term appears only when sigma 1 and sigma 2 are not the same. Here the covariance matrices are the same. So you will have x transpose sigma inverse x, right? So that's a quadratic term. That one goes away when that sigma 1 inverse and sigma 2 inverse are the same. Is that clear?
Yes, sir. Yes, sir.
Okay. Any other questions? All right. Shall we? Have we gone through the collab notebook?
Oh, yeah.
Okay. So we'll call it a day then.
Uh, uh, all right. So, but I just wanted to cover one slide.
Yeah, yeah.
Maybe we
Please go
can.
ahead. Yeah, please.
So rest of these are some examples and properties of the decision boundaries. But just wanted to talk about one important thing. So maybe we'll have to skip through these, but this particular one particular slide is important. So for now, so we were talking about these parameters, but how can we estimate these parameters from data? So the parameters of the Gaussian, what should be the mean, what should be the variance, uh, and what should be the prior probability of belonging to some class. So our parameters are mean of each class, covariance for each class, and pi is the prior probability of belonging to each class. So the way we try to find these parameters is using what is called maximum likelihood. So the likelihood is the probability of getting probability of the data given our parameters. So this probability, and then we take a log, and if we theoretically try to maximize this value, we come up with these results. So these are pretty intuitive to understand. So over here, pi k is the prior probability of some data point belonging to class k. So here, this one is an indicator function, which is one if the term inside is equal, and otherwise it is zero. So if we sum over I equal to 1 to n, so we have n data points in our data set. So if we sum over all of the data points, and then we sum over this indicator function, the inner term will be the number of terms that belong to class k, and then we divide it by the total number of samples. So this gives us the prior probability of data belonging to class k. And similarly, we can compute the value of mu. So for mu, we will find the average of all xi's that belong to class K. So how do we select the xi's that belong to class K? We multiply xi with the indicator function, and then we sum over all samples. So although we are summing over all samples, this indicator function will make sure that this summation only considers those xi's that belong to class K. And in the denominator, if we sum over, we are getting the samples that uh, total number of samples that belong to class K. So in this way, we are finding the average of all features, and that gives us the mean. And we do the same thing for the covariance. So we for covariance we do xi minus mu k multiplied by xi minus mu k transpose, and then we do the same weighted average to find the sigma k. So these are the maximum likelihood values of the parameters, and these will be useful for you in your assignment. Yeah.
So the first likelihood, when we are deriving the likelihood, it is actually, this formula is actually saying the first thing you said about the histogram normalization, right?
Right, yeah, it's very similar. Is it clear?
Can you explain decision boundary once again?
Bayesian boundary. Okay. Hmm. Okay. Maybe I can show you some pictures. So let's say this is how you have features which are two-dimensional, and you have a probability distribution. So and this the wherever you have difference in color shows the decision boundary. So out here you take a decision. So if it's red, you take decision as class 2, and if it's gray, you classify it as class 1. And how you get this decision boundary is by equating the discriminator function. So on the left hand side, the discriminator function will be greater for class 2, and on the gray side, the discriminator function will be greater for class 1, but at the boundary they will be equal. Yeah. So do you still do you get it now?
Yes, yes. Fine.
Okay.
In the last results, could you explain the T term?
The t term. So Ti is basically the class of your ith sample. So if the class of your ith sample is k, then you put it, then the indicator function becomes 1. So you have I samples, and Ti is the class of that ith sample. So,
Yeah, T for target, maybe remember it that way.
yeah.
Sounds good.
Okay. Okay.
All
Thank
right.
you, everyone.
All right. Thanks, Ankur. Thanks, everyone.